The direct shear test is an experiment that involves finding the horizontal stress a sole can handle before failure. Imagine a retaining wall. The wall and soil must be capable of fighting horizontal stresses, or else the wall could crack, slide, or overturn. Failure in this case is defined as when the specimen reaches its maximum stress and can no longer sustain that stress level. The intergranular connection is lost, and the particles begin sliding over one another. An immediate drop in strength will occur. This image displays a sheet pile wall, retaining soil horizontally. A direct shear test needs to be run on backfill material before constructing such a wall, so that a safe design and construction plan can be implemented. Let's first begin with some definitions. Normal stress is defined as the stress induced on the specimen from vertical loading. Numerically, the normal stress is the normal or vertical load divided by the cross-sectional area. Shear stress occurs on the plane parallel to the cross-section. It is the side of a cylinder, but we often deal with cubes of soil, and the top would also be considered a side. A here is taken to be the plane parallel to the cross-section, and T is the force applied to the sides of the sample. Here's an example of the end result of a full direct shear test. Each point on this plot is a unique run, for the specimen has been loaded axially and at a stress defined on the x-axis, and then sheared at a set rate. For various axial stresses, unique ultimate shear values will arise. The x-axis corresponds to an axial stress applied to the sample during shearing. The y-axis corresponds to an ultimate shear stress that the soil can handle before failure. A remolded specimen and new test run is required for each point. The ultimate shear stress at which the specimen has no load applied is defined as the soil's cohesion. The angle phi is the defining angle from the horizontal that discerns failure. It is known as the angle of internal friction. Any combined shear and normal stress that plots a point on or above the line represents failure. Any combined shear and normal stress that plots below the line represents a safe design. We will now demonstrate visually. Here's a simple depiction of a shear sample. Imagine a 10-pound load applied to the top of the specimen. Then the soil is sheared horizontally. Its ultimate shear capacity will be dependent upon the load above. Now if we add another 10-pound weight on top of the specimen and run the test again, the soil's ultimate shear stress will increase from that of the previous run. The reason for this is because higher axial loads will compress the inner grains of the soil so that it is more difficult to move them horizontally, thus producing a higher ultimate shear stress. Now if we keep adding weights, the ultimate shear stress would theoretically continue linearly increasing. If we were to plot the first axial stress and shear stress corresponding to the 10-pound load, and the second axial and shear stress corresponding to the 20-pound load, a linear connection can be made between points. The equation of the linear fit shown previously can be written in this form. Ultimate shear stress, tau F, equals cohesion plus normal stress, sigma NF, times tangent phi. The equation produces a linear line with a y-intercept at the cohesion value. This equation is known as Coulomb's failure criterion, and will be used after the series of tests have been run to extrapolate parameters, cohesion, and angle of internal friction, C and phi. A linear fit of the data points allows us to easily solve for C and phi once the test is complete. Now onto the tools that will be used during the test. First, a caliper for length measurements, an Allen wrench for the shear bolts. 2 shear bolts will be used. The shear bolts fit into the sides of the shear box vertically so that the sample can be molded. Once the shear bolts are removed, the test can be run without disturbance to the specimen thanks to the shear bolts holding everything in place. The wingtips apply a small gap between the top and bottom box so that friction due to the boxes is not an issue. The plastic end of the wingtips screw down vertically as such. The shear box slides The bottom half of the box moves along the platen while the top stays fixed to the load transducer. Next, we have filter papers that fit over the porous stones on either end of the sample. The top platen and ball are placed on top of the top porous stone. A tamper is necessary in compacting the sample to the desired degree of relative density. We have our water. We have our bowl, funnel, and scoop that will also be necessary. First, we will want to weigh the shear assembly with the two porous stones inside to obtain our mold mass. Record the mass. Assemble the box and ensure the wingtips are screwed out counterclockwise. Screw in the shear bolt so that the top half of the box compresses to the bottom half. Place a porous stone at the base or bottom of the box, then a filter paper on top. Begin spooning or scooping soil into a funnel held over the box. Pour soil over the filter paper in a circular manner and make sure that it is also uniform. Normally 3 to 5 lifts is necessary when remolding a specimen. Compact the lift with the tamper to the desired degree of compaction. Drop the tamper from the same height every time and count the number of drops per lift so that each lift can be constructed the same way as the previous. Keep adding lifts in this manner until the shear box is full. Place the filter paper, then the porous stone on top. Clean or brush off any soil that has accumulated on the box. Weigh the compacted soil and shear box, i.e. mold. The specimen will now be ready for testing. Also weigh a tear and place some representative soil in it for a moisture content determination. Place the tear in the oven to dry at 110 degrees Celsius. After the moisture content has dried, verify that the dry density is that of the desired quantity. Place the shear box into the assembly so that the bottom half connects to the geared jack. This allows the motorized jack to move along the shearing axis or bottom plane. Screw the large vertical screw into the bracket on the opposite side of the geared jack. This fixes the top box. Note that this bracket requires a measuring device, load cell, to provide opposing force to the upper half of the shear box. It is best to unscrew the two nuts on either side of the abutment at the end of the transducer arm. This gives the assembly some slack while everything is being set. Swing the vertical load beam assembly to rest on the ball. Adjust the carriage to rest evenly on the ball by using the nuts beneath and wing nuts on either side of the beam if necessary. Swing the vertical LVDT over so that the tip rests on the beam. Also ensure that the horizontal LVDT tip is touching the side of the box to measure horizontal deformations. Tighten the two nuts on either side of the abutment at the end of the transducer arm. This secures the arm so that force measurements will be output by the transducer. So make sure the nuts are snug. Remove both shear bolts from the box. Screw the plastic end wingtips in clockwise so that some pressure is felt. Do so in a diagonal manner so that the box remains flush. This separates the two halves of the box ever so slightly. Ensure that everything is tight and flush in the system. Apply the desired normal force to the sample by adding weights to the vertical load hanger. This induces vertical or normal stresses on the sample. Allow time for primary consolidation to end before shearing. Pour water onto the sample and box until the full assembly is saturated. This expels the air voids and does not allow pore pressures to build at the failure plane. Set the shearing rate on the direct shear machine. The maximum rate permitted by the ASTM standard is 0.04 inches per minute. This moves the bottom of the box at a constant velocity of 0.04 inches per minute. Set the start condition and logging type on the associated computer. Press the right-hand start arrow on the machine. Notice that loads increase, load 1 in our case, and horizontal deformations. HORZ1 in our case, increase with it. Shear the sample to a strain of 10% relative to the diameter of the sample. Failure will occur on almost all soil samples at 10% strain relative to its diameter size. Once 10% strain, 10% deformation relative to that of the specimen diameter is achieved, the run can be stopped. Remove the weighted disc from the carriage, swing the vertical load beam off of the ball, and unscrew the large screw opposite of the geared jack. Remove the bottom platen with the shear box inside from the machine. After pouring out the water and removing the top half of the box, notice how the sample has shifted during the test. This is the direct shear effect. Do not forget to record the dimensions of the shear box. Measure the diameter of the shear box, for this will later be used in calculating the cross-sectional area of our specimen. After cleaning the shear box thoroughly, repeat the molding process. Be consistent and mold the sample in the same manner as the previous run. Take mass measurements and moisture content determinations as needed, ensuring similar relative densities. For the next run, add more weight to the carriage assembly. As shown, we use twice the weight as the previous run. This puts approximately twice the normal stress on the sample relative to the first run. Repeat the whole shearing procedure. Perform at least 3 runs. Be sure each run is set up and run like the last. Logging should consist of displacements with associated horizontal loads, which can then be converted to shear stresses. The measurements of the shear box are listed in the table. With a 4-inch inner box diameter, the sample ends up being 0.119914 square feet in area. The height of the sample was measured to be 1.375 inches. This table displays the various load and displacement readings recorded throughout the duration of a run. The left-hand side column is shear force measured by the transducer in units of pounds. We can then convert this column into stresses by dividing the cross-sectional area, 0.119914 square feet. Shear stress is displayed in the right-hand column in units of pounds per square foot. Finally, horizontal deflection is listed in the middle column, which is directly read off from the LVDT. For each given normal stress, a table similar to this is logged for each run. In our case, 4 like tables were produced since we did 4 runs. To find the ultimate shear stress, simply locate the maximum within the table. Record the maximum shear and the associated normal stress. For the 4 runs, we combine the shear stress displacement data, producing this plot. The green data set corresponds to a normal stress of 7,826 pounds per square foot. The orange data set corresponds to a normal stress of 4,695 pounds per square foot. The yellow data set corresponds to a normal stress of 3,130 pounds per square foot. And the blue data set corresponds to a normal stress of 1,565 pounds per square foot. Notice how the plot displays linearity in the very early portion of displacement. Then each data set has a well-defined peak, which is the maximum shear stress. Finally, the data set tails off and converges to a constant yet failed strength. The 4 sets of data make up a complete and consistent test. After locating all of the maximum shear stresses for each run, the table above the plot can be created. By plotting normal stress on the x-axis and shear stress on the y-axis, the data set should display linearity. A linear fit is made through the data and the equation of the line is displayed on the plot. The linear fit here has a strong correspondence to the data, therefore we know our test results are accurate. The equation of the line can then be set equal to Coulomb's failure criterion, and the parameters cohesion and angle of internal friction can then be solved for. C, cohesion, is directly read off from the equation of the line. In this case, our test soil can handle 1,640.1 pounds per square foot of shear stress without any normal load before failure. Then the angle of internal friction is solved by finding the slope of the linear fit relative to the horizontal. Inverse tangent of 0.7115, the slope, is equal to 35.43 degrees. Any shear and normal stress that plots on or above this line represents the failure plane. Any shear and normal stress that plots below this line represents a safe design for the soil in question. This concludes the test procedures and data reduction sections for direct shear testing.